Okay, so let's see some aspects of what we have to deal with. We often, you always get some data, you train, you do your things, you build a model, and everything seems to work. As you said, the model is given that you are working in a learning framework where the output is the model. Most often, whatever you might do, it works well enough in your environment sandbox. And everything that you get from then on is depends mostly on the data that you used. Now, that's a brief excursus of what you got over history and the number of images that people were using for natural image data set. In the 90s, we were working with like 10 images, then we went to 1,000 and so on. When you were working with Caltech, you actually got shipped CD-ROMs. Then we went to ImageNet with 80 million images, and nowadays nowadays, probably that was like 2 years ago, which is not even state of the art anymore for given how fast things move nowadays. People were working with almost 1 billion images, which is kind of the level of the images that a 2-year-old has processed. And where do you get data? One of the things that you dealt with was crowdsourcing. So tasking humans with creating labels, let's say, of some unspecific kinds. And there is the Amazon Mechanical Turk, which takes the name of a fake chess playing robot that was developed in the late 1800s, where actually it was a human hidden inside the machine. And that's the things you get now. You go on a computer, you say solve this task, and actually it's outsourced to people elsewhere. Now the question is, of course, how can we collect good data? And what do we mean by good? We mean correctly labeled and unbiased, which we mean it not in the, let's say, the ethical term, which is a subset of this, by the way, but is gives a good coverage of all the relevant kind of data. Bias in this case is really about the a priori probability, which either explicitly or implicitly, as implicitly given by the relative frequencies of the examples that you have in the data set. And how you can work with that, you can get more and more humans in the annotation loop. And there were lots of initiatives, some where you asked volunteers to label, in this case from an animal-related database. You asked people to volunteer in their spare times to provide labels. Then there were PhD students that were like saving 1 hour a day to manually label data. There were some people doing that for fun. There was in a Wikipedia-like environment, people doing that because they felt they were helping the world. There was people that doing that like a pastime on train. And also there were people doing that for money on the Mechanical Turk in Amazon. It seemed to have lost popularity, but nowadays there is really, really lots of people doing that. All of the GPTs and so on have actually thousands of humans working in low-income countries, manually labeling every single answer and telling it whether it's good or not. Of course, you need to remember that you need to think about the human in the loop. What do you know about them? Will they work? And so let's see a couple of examples. People are biased in general. So this was paying people to just select a random number. And of course, according to humans, 1 and 10 are not random. even numbers are less random than odd numbers, and 7 is the most random number ever. Are the biases consistent? If you paid people 1 cent to choose one of the three, you got most people choosing the middle one, followed by the top one, and the bottom one was least chosen by everyone. And do people do what you asked for? And here people were paid to flip an actual coin and writing head or tails. And in this case, you got lots of likely and unlikely result. People were keeping on writing down heads much more than tails. And also, are humans reliable? If you ask humans to click the button B, that was what they got here. And so we can start to introduce the concept of dataset bias. Now, we have talked previously about all the datasets that have been introduced in the past. These are some images from different databases. You got a cow and a sheep here. You got an airplane here and an airplane here. You got cars in different databases. You get landscapes in many of them. And can you recognize whether a car is from one dataset or the other? And no human can do that in general. But surprisingly, most models learn that with extreme accuracy. Even if you don't train to guess the model, they are really able, and you just look at the inner representation, they learn some specific characteristic of each data set, which is something you would like to avoid. So now, where can mismatch occur? So this is a classic example. You go on Google and you look for student bedroom images, and well, your test data might be here, because when you curate the data and get only the ones that are labeled very well, you might introduce a lot of shift in distribution if you want. Why is that a problem? Because a poor coverage of the real input will result in errors when you will work in test time. Now, if you're thinking about medical image data, and where might you get training data set, you might get them from university hospitals with state-of-the-art machines, with patients that sometimes come from with more rare diseases and with or are from higher socioeconomic background, and the referring physicians are better trained and so on. While if you go to do an application for to release to every hospitals in there, you might have different machine, different technologists, different acquisition procedures, different patients referral mechanism, and maybe 3 out of 5 of these issues are completely irrelevant, but you don't know which ones are them. So this one is an example that I've shown you. That was a model trained to colorize images, and this was the performance on the training data set. And this was the performance on some unseen images when this model was put on Reddit. You can see that it was just giving out sepia colored images. Or even weirder examples that they had found, when they tried to colorize these 2 images, they got a pink hue here. And it turns out that in the data sets, a lot of dogs had their tongue sticking out. Now, where does this come from? It comes from what can be discussed as a domain gap between the probability in the training distributions and the probability in the testing distribution. So, like to make this example, if you train on all these animals here and then you work with this image here, these are really different. That's the classic example, which is super simple to understand when you're working in one dimension. But as you know, from probably every single course in data science, we are working in extremely dimensional spaces. Now, this is a classic example of what happens when you have if you take the A data set and split it in train and test, that's the accuracy on the test data set that you might get. While if you use a completely different training data set and validate on the same one, the two errors starts to converge only when you have a very large number of training points. Now, this is something that happened to me 1 week ago. I downloaded from the internet a very large model trained with super high levels of data augmentation, which we will go further into later. It was a model that this is just a validation task to see that everything was working normally. It was like a very trivial one for that model, which is predicting the age of a subject from an MRI on the brain. And that's what I was getting on the training data set. On the training data set itself, you might think that 6 years of mean square error is good, but I mean, you're precise enough. But if you think well about that, well, first I've also taken the average mean difference. And we have 5 years of bias. This is the identity line, and we are always systematically higher. And when you're training using the mean square error, this shouldn't ever happen, because the really first things that the mean square error does is getting the mean of the two data sets to be equal. Maybe it doesn't predict anything. You get a flat distribution here, but at least with the same means. And also it was, okay, so the mean square error, root mean square error was highish, but still acceptable. But it was on the training data set, it should have been better. And indeed, this software, when loading the images, was running a pre-processing, quite standard one. And after really a lot of, getting text editors and, because one was a notebook, one was a Python file, text editor, and doing the differences, I found the difference between the code, which was actually the same everywhere, except for the pre-processing transform, going from the DICOM image on disk to the array given to the model. There is a single difference, which is this flag here. That was, and I got the difference is now, as you expect on the training data set, when you've kind of overfitted, the mean difference was practically 0, and the root mean square error was very low, probably too low to be true, but I'm working on the training data set, not even on the validation data set. So when this model was resizing images to some common shape, some common format number of pixels, and in this case, it was using the default interpolation, which is the way to actually interpolate the images. We haven't seen that much in the course. And that this was using the default transform, and this was using the trilinear transform. And to my opinion, as someone who has developed interpolation algorithms not developed, they are very standard, but who has used the interpolation algorithm for more than a decade, these two transformations don't make any practical difference unless you are really going to, like downsampling or upsampling to a factor 4. And in both cases, they are not really changing the relevant part of the information. Yet somehow, given how this model was learning patterns, this was enough to get a very significant shift in the results. not just increasing the standard deviation. If I got a standard deviation higher by 2 years, who cares? So it's really difficult to predict what parameters your models will start to focus on. So indeed, there are lots of initiatives about how to make models fair. And let's see some kind of why these shifts occur. Now, as an example, where I took this material from, there was a disease where most of the natural species are concentrated in the world, like for vegetables and animals. Of course, they are mostly in the rainforests. And if you look at the species that are most represented in the genome databases, they are where most of the universities are. They are in Europe, in the coast of the US. Like even within the US, you get most of the nature being here in the middle, and most of the plants for the database being on the coast where you have all the research centers. There was this very interesting work about the effectiveness, the replicability of models when used in the practical applications. And these studies that you can download from Google Scholar was applied to very different scopes. Like they took a model that was trained to classify pathology images, a model that was used to recognize the animals in the environment, some used to understand demographics, some used to classify product reviews or anyway text. This was for automatic content moderation. This was for protein. And it turned out, sorry, I cropped out the table, I guess, that in every single one of these different, completely different tasks, in the application when downloading a software that had been published online, they got like at least a 10% reduction in performance. Now, so why is that a problem? Because of the lack of robustness. It's relatively easy to understand that if your training data are here and your test data are here in your space, the model prediction will be highly irresponsible, the classic hic sunt leones from the Latin maps. However, you need to remember that you are working in a super high dimensional space, and in a high dimensional space, probably you've seen the course of dimensionality, actually every point is far from every single other point. So the coverage of the space is intrinsically hard. So we have seen this concept of overfitting, where you might get learn way too well the data in a non-representative way. But what happens if we go way outside the distribution? This is the bias. And if the model is biased, of course, it will not work well. This was copied. Now, there was, with older models, lots of research we say older, but we are thinking about 5 years ago, about adversarial examples where people was taking the gradient of the loss and looking for super intentionally weird images that got classified as something. Like in this case, you got these random patterns that were classified as a penguin, as a starfish, as a baseball, and so on. And you can think about, when you're working with neural networks, about different depth levels, and you can think of 3 categories of features. You have useless features that don't help the model in any way. And you have robust features that correlate with the label even after perturbation. Here you can see, I guess this is the same dog. You crop it in every part, you even mask it out, but keep the shape, and they work. And there are some non-robust features that are correlated with label, even very highly correlated, but the correlation can be flipped using a perturbation. And as we have seen in the case that you are able to recognize the training data set, this is a feature that should really be relevant. However, that's a kind of example of correlated with labels. What you do in a normal training is that your optimizer minimizes the loss for all the data and label pairs, and this will learn both robust and non-robust features. However, what you want is a model that should be stable under adversarial attacks, and therefore you want to teach invariance to some non-robust features. As an example, what you can do is to use data augmentation. I've already talked about it. It's sometimes thought of as making a bigger data set, but what you're actually doing is telling the data set, the model, what not to learn. And in this case, if you want to do a classification of a scene, mirroring should be relevant. Random crops, of course, should be very relevant, and even some shifting colors. And like in this case, if you start to do that with image category, of course, that's super easy. If you start to doing training, croppings, flips, and so on, the training distribution starts to broaden. And you can go all the way to introduce even blurring and jittering and so on. And of course, you need to be very careful, and this is something that is really, really task specific. You need to know your data set, you need to do your task, and so on. For example, like if the label is correlated to the color of the image, like I don't know, you need to classify birds, and the color of the feathers are relevant, you don't want to change that. Or if you are doing a segment, or sometimes you need to change the label, like if you are doing a segmentation, pixel-wise recognition of objects, and you move the object of interest, you should also move the label. Like if you flip left to right, you should also flip left to right the mask. In Keras is very, very easy to apply augmentation. You can build an augmentation model, which is a model that isn't trained, using the sequential API, and you just add some layers. And there are special layers that can be used for image augmentation, and I've copied here all of the layers that you have. And as you see, you can be very creative. Because they can change the brightness, and you can make lots of differences to the color. You can change the contrast. You can do elastic transform, which means distorting the shapes locally as compared to the zoom, where you might at most do a different zoom on the X and Y axis. Here you can even distort the shapes, and you can do the blur and change the hue, invert the colors, and do some perspective, like if you take the image shifted from up or down, and so on. Now, as I said, you can easily be super creative, but you must know very well your dataset properties. And all of these layers actually have been developed for natural images. When you're working with medical images, most of them don't really apply. So what you want to do is you might need to do some combination, and when you go to different projects, you might you can even write your own functions without too much difficulty, actually. Because you might, I don't know, change the intensity scale, but the contrast is probably not something that you want to act on. And some minor blurring might be relevant, some addition of noise can be relevant, but up to a point. So the issue is that we always want one model for all data and the task, but we have a poor robustness of neural networks because the network starts overfitting. We have data bias where the training data does not cover the entire data distribution. And even you might have adversarial attacks where human unnoticeable change to the data can fool the network. And therefore, you can improve these up to a point using adversarial training and data augmentation. So how can we go much farther than that? We need to go to do better than supervised learning. Suppose that we want to relabel the original ImageNet 1.4 million images. And on top of all the other considerations, how much will that cost? We have 1,000 for 1,400,000 images, which is not that big data set nowadays anymore. Let's say that a label takes 10 seconds an image, which is relatively fast. That we pay this person doing that $15 an hour, and that's $175,000. And this assumes low pay, single annotator, no overhead. You probably need an office, a computer screen, heating, healthcare insurance, taxes are probably included, and so on. And no benefits and no setup cost. And for all of that, you need to assume that this person is working both fast and reliably using a single one. And you start to see the issue. Even if with nowadays budget for AI, probably that's not even where a training run can cost $30 million. This kind of using $500,000 for labeling is not really unimaginable. But suppose that you want to go to 1 billion images, and we have data set of 1 billion images, that's like $40 million. So the question starts to be, do you need good data, and what can you do with bad data? And this is extremely relevant in medicine, because in medicine, when you say this technique is super precise, you might talk about 90%, let's say 90% sensitivity and 85% specificity, or maybe more likely 80% specificity. Which means that really in 100 images, you have probably 15 or maybe even 20 wrong diagnoses. So our ground truth is poor to begin with. So this question is really important. And what do we mean by bad? Incorrect labels, no labels, biased, unrealistic, or outright fake. And the recent trend, you might have heard of that for sure, is to just scrape massive, immense amount of raw data, images, text, whatever, from the internet, and distill knowledge from that. And what's behind that? It's the concept of transfer learning, where then you can divide your task in pre-training and fine-tuning. In the past, what people might do was to get an image and extract specialized features, which were edges, first of all, then orientation, then histogram, and then clusters. That's relatively easy to interpret. However, this has a lot of issues, like you need a lot of domain knowledge. It's work relatively well, for low-level representation, but it's difficult to represent high-level abstractions. Where did we get from here? From in convolutional neural networks, we have a convolution that outputs a representation, followed by a second convolution, and so on, so on, and so on, followed by a classification layer that outputs a class. So what do we get if we look at the output of the first convolutional layers? We get these kind of images, and we see some edges and so on. If we go to this second layer, we give this kind of stimulus in input. We have some shapes here. We can see that these shapes start to appear as output of the layers. Here, they have been just choosing the most active feature layer. If we start to go deep and like we get some shapes, some part of the bodies, some faces and so on, we can see that they are somehow represented. We can see that here even we have writings and they appear here. When we go to the deeper layer and so on, we start to see like faces of dogs, of contours and so on. And even more when we get to the deeper layer, we see very well the faces of people, of writings and so on. Therefore, we have the concept that we have previously mentioned, that the deeper we go, the more we go to more abstract features. We go from edges, like we were, which was the first kind of extraction in handcrafted feature extraction, to very deeper representation. However, what we have here is that we have some representations that are hard to interpret, and however, they reduce the need for domain knowledge and feature engineering. But we have lots of multiple levels of representation, and most important of all, we know / we infer, we think that representations are transferable. And that's really the single most important part of the discovery in the deep learning revolution. So what you can do is to pre-train learning of representation of huge, large-scale data sets, and then you can fine-tune on a very small-scale data set for which you know the ground truth for downstream tasks. That's because it allows deep learning for a small data set, and it allows deep learning to benefit from almost all tasks. Now, let's see how this works in practice. With what the people used to do was pre-training like on some large-scale data set, and what the people used to do in the past was generally a supervised task in the past, which meant like learning image classification. Nowadays, we can work with things like contrastive learning, where you can, what you can do is unsupervised learning. You don't need a label, so it doesn't need to be accurate. Then when you want to do fine-tuning, you just take all of the layers and you transfer the weights to some specific task on some small-scale data. Your training will be very short on some with lower learning rate. And it enables you to use a very large model without the risk of overfitting, even on small data sets. And what you also can do is the partial transfer, where you just get some layers. The most common thing, however, nowadays is to use keep all the layers with the exception of the head. And then you can just initialize some new layers. And you can also freeze the initial layers, because if you have really few data, it can reduce overfitting. You can save memory, speed up training quite a lot. You do that with you can do some so-called network surgery, where you repurpose a single model for different tasks. Like you train a model on classification, and then you use it for segmentation. You even get a completely different shape of the output. Now, transfer learning is, to summarize that, exploits some deep representation that are transferable. So you pre-train on large scale data and fine-tune on small scale. And these are the common tricks: training, fine-tuning, partial transfer, and so on. Now, what's behind, what's the most important things that is being done nowadays? Let me check which. Okay, just two slides because I thought I would have been slower. Anyway, what you can do to really exploit the massive data set is to use what once was called unsupervised learning, which means you don't have any label or prediction to be done. But nowadays, it's more fashionable to call it self-supervised. It means that the model learns by itself. What is being done to do that is to pre-train a network on a pretext task, a task that you don't really care for, but that you envision for some reasons, mostly empirical, that it will force a model to learn the most effective representation of the data. One of the most used strategies in the past, which can still be very relevant for some specific task, is that of the autoencoder. So you get an image, you build two neural networks, one an encoder feed that goes from the image to a vector of features. And for autoencoders, properly said, this vector of features was small because you wanted to enforce a very compact representation. But if you just want to do pre-training, this doesn't have to be small. And by small, I mean like 100 features. But if you don't want it to be small, you can use 1,000 and so on. And then a decoder that from this feature predicts the input itself. So you have an image, even if it's small, it can be 500,000 pixels. You describe it using 500 numbers, and then you go back from there to the original image, and you, as a loss, you use the mean square error between the reconstructed image and the input image. And especially if you have a very large data set, this will be extremely effective, actually. And once you have done this, once you have trained this encoder, I mean, if you think about the lecture about denoising, if the image is corrected by mean square error, by Gaussian noise, this is really, there is a statistical reason to use this, the mean square error. This is really forcing the images to be as close as possible. Once you have trained this encoder, you can just take this vector of features and attach later a downstream task model. And it sometimes is theorized that here you can just get the vector of features and use a trivial classification, like a linear classification. It's heuristically thought that oftentimes the representation that you get should be linearly separable. So here you just do an SVM without kernels, you get a linear regression or so on to do a classification. So what you just do here is to cut off the decoder. You don't need it anymore. You take this vector of features, and then you can do some linear classifier, k-nearest neighbor, or some fine-tuning for another model if you want. there has been a lot of research in what this pretext task can be. I've left you the links from which I took these two slides, and it's actually like hundreds of slides about that, because this is extremely effective. And so what can be this pretext task? You can just predict the part of the input signal, so you can have the autoencoders, either sparse or using a very complex representation, or denoising, or even masked. You need to learn a mask representation, so you delete part of the images and you want to reconstruct the full image. And it has been found that like with images, you can crop out 50% of the input in random patches and still predict the output. And that's how they trained language models. However, with language, they found that you can crop out like 20% of the words, while with images you can you can train successfully by deleting more than 50%. Then there was other things like trying to predict color or predict masked parts, and because for a network to be able to predict the color of an object, it needs to learn what objects are. Like if it predicts that bricks are red, it is because it has really seen lots of different materials. So even if you don't care about colorizing grayscale images, that can still be effective because it forces to learn some representation of the word model, which is unrelated to the most specific task. There are others. It's about predicting something about the input signal, like one interesting one that I found was trying to predict rotation. It was getting images, natural images. They were being rotated by 90, 180, or 270 degrees, and the model had to predict what was the original orientation. And again, this forces the network to learn some human context, because if you take a picture of a tree, it needs to know that the leaves are on top, and so on. If you take a picture of a statue, the head should be on the top, and so on. Or I guess that's still the most used one now is contrastive learning. You take in every batch of the training, you take like 30, you take 3 different 2 or 4 or whatever augmentation of an image, and you use you forces the representation, different augmentation of the same image to be represented with the same representation using basically a cross entropy, and that of other images to cluster together. So you say that however I might augment an image, put all of the augmentation of the same image together and of other images farther apart. And this has been found to be extremely effective. Now, let's talk about distribution shifts. What do we mean by that? So in an ideal world, we will have this distribution of data as a sketch, but most likely in inference, the relative frequencies of many objects will be different, and we have some slightly different cases, and we will we will have less of some that we have seen, and so on. That's the case that I've shown you before, and well, okay, here I have the results on that. And that was the so-called out-of-distribution accuracy. You can see that it lost 22% on pathology examples, on classifying plants 13%, on recognizing differences in built environment also it went down. Bioassay prediction went down, and also for this recognition of animals in the environment. Now, to recap these robust and non-robust features, and let's remember what we can do. So let's just recap what we can do is augment your data, adapt your learning to the target distribution, and maybe using unsupervised algorithm. And of course, the best things you can do in general is get training data that is representative of your test domain. However, just to conclude with the last two slides, and there are some other validation issues. Suppose that you take a very classical example, either the ImageNet dataset or the CIFAR-10 dataset, and you take lots of published models that are present on the internet, and you validate them on other datasets. These have been validated on the blind ImageNet or CIFAR-10 dataset, and it turns out that systematically, this is, I don't know, like 50 models, when they have been tested on a completely different data set, still on the same task, they had less accuracy and they had a specific trend. And the same for, that was the CIFAR-10 and that's the ImageNet. You get a quite stable drop in accuracy. And there are lots of issues possible for that, including, there are many even practical issues. You have researchers publishing codes on GitHub and you don't really never know how they run it, and probably they choose the best training run that they got, well, best validation run. And also in this competition, you have, I don't know, 100 teams participating. If you take even the testing, not even the validation performances, in some way, it's kind of self-selected to be the best among 100. And indeed, there was this paper from 2023 where some researchers from Princeton take 22 machine learning papers in 17 different fields, completely different from each other, and they found that involuntarily there was data leakage in the vast majority of them. So sometimes, even if you don't realize there is some data leakage from the training dataset to the testing dataset, because maybe you use it for initial data cleaning or to select the best pre-processing pipeline. Even in what you think is an independent task, sometimes it happens again. So it's a really, really hard topic. So just this is the end of this presentation. This is, as we will see now, machine learning for medical images works remarkably well, because we have thousands of software working in the clinical field nowadays, but still you need to remember that when you get 99% accuracy, in generally it isn't. It's something else. Okay, questions about that?